Welcome everyone to the last afternoon of this conference. This session will be dedicated to imaging the biggest black holes on the sky. We think it is the one at the center of the Milky Way galaxy, but M87 is a contender for being of comparable size. And we'll start with a talk by Sheperd, Doeleman, who leads the observational effort. He's the director of the Event Horizon Telescope. Sheperd.
Okay, thanks, Avi. It's a real pleasure to be here. The BHI brings together a lot of different communities, and one of the communities it brings together is the Event Horizon Telescope every once in a while. So we've had some meetings here, and it's really a wonderful meeting point for many different communities to come together to engage in this project. And this is a project that we're really passionate about. Simply put, we're trying to take a picture of a black hole to see what it looks like very close up with Schwarzschild radius scale resolution. If we could do that, we could address problems at the frontier of GR, general relativity, and accretion, and space-time. And essentially, we're doing this by linking a web of radio telescopes that span the globe using a network of atomic clocks and very high-precision electronics. And we hope to make an image that maybe has echoes of this, which is an accretion flow and the last photon orbit around the black hole. And I entitled this The End of the Beginning because after a period of development of technology and after a period of doing precursor observations, we feel that we are close to making the first attempt at making this image. So what we're after here are really strong GR signatures. We want to get to the regime where GR determines what you're going to see, not how you light up the space-time. And no matter how you simulate or model the region right around the black hole, in the millimeter wavelengths, you always see this shadow feature here, delineated by the last photon orbit, the orbit that light actually takes as it curves around the black hole. The onrushing emission here is Doppler boosted to you, so you see a bright side and it becomes a crescent shape, like during a solar eclipse. And the radio emission comes from the synchrotron process, so we know there are magnetic fields there and relativistic particles. So we're looking at primarily millimeter wavelength photons. The shadow size for the two objects that we hope to image, Sagittarius star, the 4 million solar mass black hole in the center of our galaxy, is about 50 micro arc seconds across. That's about what you would see an orange to appear like on the moon. About 2,000 times better than the Hubble Space Telescope resolution. And for M87, which is a little more than a factor of 1,000 times more massive, but it's farther away, it would be 40 microarc seconds. So we need to build a telescope that is extraordinarily powerful. And a number of people have contributed to the development of the analytic and theoretical approaches to what those shadows look like. Now, in addition to the light, the black hole dynamics are also really interesting, right? Because matter can't orbit a black hole any way it wants to. The innermost stable circular orbit depends on whether you have zero spin, whether you're prograde, whether you're orbiting in the same sense of the spin of the black hole, or retrograde. This shows the size of the innermost stable circular orbit as a function of spin, and it ranges from 1 gravitational radii up to 9. And then this is really interesting. This is the time it takes to orbit the black hole. And this is very responsive to spin. So at a spin 1, you're looking at 4 minutes for Sagittarius star and 4 days for M87. 4 minutes to orbit around a black hole that weighs 4 million times what our sun does. And if it's in retrograde orbit, it takes just an hour. Still pretty impressive. But this is a way that one can get a handle on spin just by looking at timing of resolved observations of a black hole. So we're in a Goldilocks situation here. We need to get 50 microarc seconds resolution, and you can do that if you build a telescope as large as the Earth and you look at millimeter wavelengths. Okay, so this is basically the angular resolution equation. We need to see through the Earth's atmosphere. It's turbulent, but the opacity is less than 4 millimeter wavelengths. So we're okay so far. If we want to use millimeter wavelengths to observe these things, we're good. We have to see through the scattering in the interstellar medium, and it turns out that scatter broadens the emission with a lambda squared law. So a point source appears puffy, it appears out of focus. But that reduces the shorter the wavelength you observe at, until finally at 1 millimeter here, you're poking out through the scattering. You're seeing the intrinsic structure, the brightness around the black hole, and it's largely unaffected by scattering. And this, I show this because there's a lot of historical observations that really we're building upon in this effort. And then the accretion flow has to be optically thin. You've got to see deep into the gravity well, so you've got to see through the 100 billion degree gas that surrounds the black hole. And millimeter wavelengths do that. In fact, most of the energy from the Sagittarius A-star black hole comes out in the millimeter, and it begins to turn over here, becoming optically thin. That's where you can see through all that hot gas. So everything is coming together. What we didn't have was the sensitivity. We needed bandwidth and large apertures, and that's what we've been working on over the past decade. Short wavelength VLBI is the way we do this. We link telescopes across the globe with atomic clocks at each one to timestamp the data as we record it from the same black hole, same point in the sky. We ship the disks, hard disks that record the data on 747s, because you can't beat that bandwidth, to a central correlator, one in Germany and one in MIT, and we create a large interferometer as large as the Earth itself. That's how we get the raw magnifying power, and we've harnessed commercial units now. We buy this stuff on Newegg, we get it from Amazon, and we put everything together and we network it. This is what has allowed the Event Horizon Telescope to get the bandwidth we need to get the sensitivity we require. So we made some first observations in 2008. We linked these 3 telescopes together, and we were able to fit the data to a Gaussian curve here, showing that we were looking at a size of the emission around Sag A star in the millimeter of about 4 Schwarzschild radii. That was really, I think, the moment when we thought we could do this, right? We'd been preparing for a while, we'd been thinking about it, but seeing something this small, the size of the shadow, set us on the path to improving on this so that we could make true images. And there have been a number of really interesting results so far. Vincent Fish saw horizon scale variations. We looked at M87, saw the same size structure. Kazu Akiyama observed it, Sag A star, when there was a TeV flare, so there's this multi-wavelength angle on these observations. And Michael Johnson, who you'll hear from in a few minutes, discovered ordered magnetic fields at the horizon of Sagittarius A star. So just with a few telescopes, and we're building it out to this, right? We want to get world domination. That's what it's all about, right? We're not going to be happy until we've colonized the moon. I'll get to that at the end of the talk, actually. And then we're going to Greenland this summer to outfit that site with an atomic clock so that we'll have both poles. We'll be able to look at M87 from the north and use South Pole to get Sag A star in the south. Now the key thing here, and the reason why this talk is titled The Beginning, the End of the Beginning, I knew I would get that wrong, the end of the beginning, is because we set ourselves a goal. We said we need to get ALMA. ALMA by itself increases the sensitivity of the Event Horizon Telescope by a factor of 10. And we started phasing up ALMA, linking all 66 dishes, each 12 meters diameter, to make one large effective dish, 85 meters in diameter, about 6 years ago. And it's complete. And we've now used it for observations with the EHT. That's why this is the end of the beginning. So we're phasing up very, very well. This shows the noise and the phasing. It's almost nothing. We're getting wonderful interferometric fringes between Chile and Spain. This is truly, really extraordinary. And hats off to the whole international team that made this possible. Here's the key message from this talk. After about a decade of thinking about it, this April we made the observations we've been waiting for. We used 8 stations, OPEX near ALMA, the South Pole, LMT in Mexico, the SMTO in Arizona, the JCMT and the SMA in Hawaii, and Pico Veleta in Spain. And we got 60 hours of ALMA time to observe with. Over the course of about 10 days, we triggered 5 days waiting for the good weather. And that is one of the most agonizing things you can do in this business, just wait, right? Because the weather can be really good at a couple of sites, but if it's not good at all the sites, as my mother would say, you're SOL, right? So we waited, and the specs were really impressive. We were recording at 32 gigabits per second. So we recorded about 4 petabytes of data during this entire run. And I'm happy to say the weather was fantastic. We really lucked out with the weather, and we think we have at least a few epochs on both of the sources where we can expect some very interesting data. Now, in addition to the EHT data, we were very surprised and also overjoyed that a number of different facilities wanted to observe with us. So in red and orange up here are the EHT observations, and you can see we also had TEV, Cherenkov detectors observing with us, X-ray telescopes, and lower frequency radio. So a lot of different facilities swiveled to go look at these sources at the same time we were, and we expect there'll be some very, very interesting synergies here if Sagittarius A star, M87 are seen to exhibit flares. Now, what can we do? So I would say this is maybe a little optimistic, but I think it's within the realm of possibility. This shows the baseline coverage that we got in 2017, and we think that with this simulated image here, we could realistically produce something like this with ALMA. So we're in range of doing what Dimitrios wants us to do, see the shadow and measure that. We're trying different modes of measuring and imaging. Mostly imaging. And Katie Bowman, who's in the audience, runs the VLBI imaging challenge. We look at a lot of different ways to image, and we're just looking for the best one, and a number of different people contribute to that. Here's some examples. Here's one. Here's some of the results from the whole community on the first imaging challenge, and that's the truth image. So in a blind test, people are doing pretty well when there's only thermal noise. Here's the next one. So this is a little bit harder to image, right? And that's because the image is a lot noisier, and we've also added atmospheric noise. So we are testing still some of the imaging algorithms. And then this is the last one. Can you guess what that is? We decided to put, Katie decided to put a snowman in the center of the galaxy. And I think it's really interesting that all of these different methods came up with something that you kind of look at and say, that's Frosty, right? And maybe there's a cultural bias built in here, but the Americans said, that looks like Frosty. So this is the kind of stuff we're working on to refine algorithms. Dimitrios and his team have been working on feature extraction. So instead of just looking at these crosscuts here, they take gradient finding algorithms like radon transforms, and they can tell under certain circumstances what the size of the shadow is, and that's what tells you if GR is or is not correct at the black hole boundary. And this is an active area of work. We can also time resolve black hole orbits. That's what I talked to you about before. If you just look at non-imaging raw VLBI data, which is the closure phase, the interferometric phase summed around a triangle of baseline, just a raw number that you can plot on a strip chart recorder, as a hotspot or inhomogeneity, which I think Avery is going to talk about in a few minutes, orbits the black hole, you see this heartbeat kind of signature. And these are sample synthetic points in the black here. And at 4 gigabits per second, you can follow it. But at 64 gigabits per second, what we'll get to next year, you can really follow it. And in addition to this, people are looking at turbulent signatures. And we hope to learn something about the accretion and potential orbiting dynamics around the black hole. It is much more complicated than that. Actually, I don't know how to make that run. Take my word for it, this is actually an animation by Hotaka Shiokawa, and it orbits, and it looks very, very nice. And I think you'll see it in Avery's talk, perhaps. And a number of people listed here, Freek Rolofs, Hotaka, Raquel, Leah Medeiros, and Junhan are actively working on these time domain techniques. Some of them are here at the BHI visiting us. So here we are. We've grown from a small ragtag group of ruffians going up to the top of telescopes with duct tape and wire, making things work, to a larger ragtag group of people going up to the tops of telescopes. We're still as scruffy as ever, but there are more of us, and we're working actively on many different areas of analysis, of technical advancement, and organizing the whole effort. And I would add that Dimitrios, who's here, is the project scientist. Remo Tolanas is the project manager. I'm the director, and we have a number of people serving on various councils that are of immense help. Charles is on the Science Council right there, and Avery's on the board. This is really an introductory talk, because there are 3 talks coming after this, which are going to go into a lot more detail. But thanks to the whole team here, many different funding agencies and team members. Some of the teams here, this is Dusan Pijakovic, who's actually our Gordon and Betty Moore Foundation project officer. He couldn't resist coming to the top of Mauna Kea, and here he is, hopefully not really fixing the hydrogen maser, the atomic clock there. I really hope that's not a true screwdriver. These are some people at the top of Mauna Kea. This is the crew that we sent down to Mexico. And this is the intrepid crew led by Dan Maroney from University of Arizona, who went to the South Pole. That's just some of the team. So now we're at the beginning of the rest. I kind of rushed through that, but let's take our time for this 1 minute. So the data from this last run is now coming back to the correlator. We don't have it all yet, but I can say verbally that it looks pretty good. We see no showstoppers. Jim is saying, say more, get in trouble. So far, all the telescopes that we have looked at worked. That's what we're happy to say. So the Event Horizon Telescope is working. We're continuing the development of the analysis pipelines, but we're not stopping there. We're building out to 64 gigabits per second, and that's a rising tide that lifts all boats. So the whole EHT will get a factor of root 2 more sensitive by next year, and we're adding Kitt Peak and going to Greenland. The next talks, Avery and Charles and Michael will go into detail on imaging and time variability and accretion flows. And in the future, we're not stopping here. The EHT started with a vision, and we have executed that vision, and now we're working on new vision. Because we have some really interesting data to work with, but we're asking ourselves what comes next. And what comes next probably are smaller dishes. We can populate sections of the planet that don't have millimeter wavelength telescopes right now with small, versatile, portable dishes. And they'll be viable because ALMA is so big that you always have a sensitive baseline to ALMA, right? So for relatively modest cost, you can significantly increase the imaging capability. And then the final frontier, Andrew Shale, Katie Bowman, and Michael Johnson did a very interesting simulation recently in which they looked at going to 345 gigahertz, the next jump in frequency, where you get much better angular resolution. And you see through the scattering much better. The magenta curves here are Earth baselines. The blue is a low Earth orbit satellite of very modest size, about 6 to 8 meters. And when you try to image with just the Earth size, just the Earth sites, you can kind of maybe see the shadow. But when you get all those UV points, because the satellite orbits once every 90 minutes, you make a beautiful image. So this may be where we're going in the future. Thank you very much.
You take some questions, Jerry?
Will you have any time resolution, because the accretion may be variable on the black hole scale?
Yeah, so I assume you mean for Sagittarius.
Which is on the order of a minute.
Yeah, so GM over CQ for Sagittarius A star at 20 seconds.
Yeah.
That's the light crossing time. So because we have ALMA, and all I'll say is that the data are really interesting. We have a lot of signal-to-noise ratio. We expect to get a lot of signal-to-noise ratio. I think we'll be able to look at time scales much less than GM over C cubed. I think. I'm not making any promises, but I think.
Erwin?
What orbit are you thinking of for your 8-meter dish in Earth orbit? You're thinking of what inclination?
Oh, well, that's very interesting. This was done for the International Space Station. We just picked that because we happen to know the ephemeris for the International. We are not suggesting we're going to bolt an 8-meter dish onto the International Space Station. But this gives you some idea of how quickly you fill up the UV plane when you orbit the Earth every 90 minutes. And there are complications, of course, that you know about, Erwin. You know, you need to have short integration times because the satellite is moving, right?
Shep, when looking at the image on the left, which is the best we can hope from the ground on Earth, the main concern is that we don't know where the black hole is. Would you like to comment on that? Because, I mean, in theoretical calculations, you often have an X where the black hole is supposed to be. What do we do with the image?
So this is a little misleading because not only is this a higher frequency where we have fewer dishes on the Earth, but we've taken 2 of them out. So we can actually do better than this at this frequency only from the Earth. We purposefully took 2 dishes out to make it very bad, and then we rescued it with the satellite.
I see.
And that's what's happening over here.
Priya?
To elaborate on, so you've taken into account the Brownian motion that the black hole itself will be sloshing around.
You mean due to the mass distribution around the black hole?
Yeah.
That's
Those-
very slow.
We have not done
So,
that, but I
okay.
think that's going to be very,
Very
small
long time
compared.
scales? Okay.
Yeah, also compared to the
What?
variations in the accretion flow too.
If you use the equipartition to estimate the speed,
Yeah.
we're talking about speeds of order, kilometers per
Well, I
second,
guess it's
because it's 10 to the minus
sub-relativistic
3 of the
stuff.
stellar speed. And, that wouldn't introduce much of a change during your observing time.
Yeah, and I
Was
think
there-
Mark Reed did some very sensitive measurements at 7 millimeter, and he didn't see any wander.
Well, we actually have a paper with Mark Reed on this subject.
yeah.
Any other comments? Jonathan?
Sorry, this has to be a technical question, but there's a signal-to-noise ratio in your satellite-assisted image. What's the downlink bandwidth assumed from the satellite?
Where's the signal?
No, there's just, I'm assuming that the simulation is done.
Yeah, for the purposes of this simulation, this is, I think, 64 gigabits per second.
Per second.
So
So the question to ask is, can a satellite spit out that much data over a downlink?
Well, we're always pushing the boundaries, Jonathan. I mean, if it was just something that we had to, buy off the shelf, we would do that. But this is going to require development, but happy and glorious development. Right?
That's right. I'm not trying to catch you out. It's a serious question.
Yeah, I think this was 64 gigabits per second. And by the way, this is Jonathan Weintraub. He kind of leads much of the technical effort on the Event Horizon Telescope.
Shep, will we need to know the location, the position of the satellite within a wavelength? Because that is better than current GPS gives us.
Yeah. So you do for the satellite what you do for the Earth-based telescopes. You also don't know where the Earth-based telescopes are to within a fraction of a millimeter. So you solve for it by searching on a grid of delay and frequency, and then you build signal-to-noise ratio, and then you find out where essentially the telescope is. You do the same for the satellite, but you also solve for an acceleration term. So it involves some more fitting, but you can still get it.
Yeah, it's a cooperative target, unlike military targets that run away from you. Yeah.
Oh, that's another tie-in I hadn't thought. Maybe get some money from the Air Force.
Any other questions or comments to Shep? If not, let's thank Shep again.
All right. So I just want to start by thanking the organizers, particularly because there are lots of locals who could have given this talk. And I'm going to try and convey a sense for what goes into the models for what EHT will be observing. And I don't know if I have to explain this, but the idea is that black holes have no hair. Okay, thanks. So, and this is work done with a whole cast of collaborators. So EHT will be looking mainly, or has looked mainly, at the largest angular diameter black holes, which are Sagittarius A star, the galactic center, and M87. We know quite accurately what the angular size of the black hole in the galactic center should be. We know less accurately what the size of the black hole in M87 should be. So the mass is uncertain by about a factor of 2. There are gas masses which center around 3 billion solar masses, and there are stellar dynamical masses at around 6 billion. So we don't really know how big it's going to be. These two sources sit in quite different regimes in terms of physical processes around the black hole. So for the Milky Way, the accretion rate in units of the Eddington rate, which measures the relative strength of radiation force and gravitational force, is around 10 to the minus 8. So it's essentially a non-radiative system. Whereas for M87, it's much higher, and we think radiation may play some role. So I'm going to talk a little bit more about Sag A star and almost nothing about M87. So we know a great deal about Sagittarius star. It's probably the most observed black hole in the universe. As Shep mentioned, the characteristic timescale is about 20 seconds, so it will evolve or has evolved on the timescale on which it was observed. The luminosity is small, and most importantly for the models, we already know about how big the source is. So we know the size in steradians of the source. We know the fluxes at many different wavelengths. We know the linear polarization of the source, circular polarization, and something about the fluctuations of the source at both millimeter wavelength and at 2 microns and in the X-ray. Okay, well, let me try and situate the galactic center black hole a little bit in our galaxy. We're out here at 4 × 10⁻⁻⁻, GM over c squared. And so there are 10 orders of magnitude in dynamic range going into the galactic center. And if there are any cosmologists in the audience, the microwave background is 6 orders of magnitude off to the right. And most of what we're focused on, most of what the modelers are focused on, is the region immediately around the black hole, within about 100 GM over c squared of the event horizon. And we're focused on that because almost all the emission arises in this region. So the temperature goes up steeply as you move in toward the event horizon. The density and the magnetic field strength all go up steeply as you move in. So all the models are focused on the region right around the black hole. Okay, I also want to put this in the context of other black holes, other accreting black holes in the universe. So we don't know what all the parameters are that are important for describing black hole accretion, but certainly one of them is the accretion rate. Here I've plotted this in terms of the Eddington luminosity, again, connecting the gravitational force to the radiation force. And Sagittarius star is way down here at the left end. M87 is somewhere in the middle, and the really bright active galactic nuclei are off to the right. So these guys are in what's called the radiatively inefficient accretion flow regime, and off to the right is in the thin disk regime, and M87 is somewhere in the middle. Okay, so what goes into modeling the plasma that we see around the black hole? Well, there are a lot of inputs, and some of them are fairly uncertain. So first of all, we need a metric to describe the space-time around the black hole. We're using the Kerr metric, but others have investigated alternative metrics. So we need a spin and a mass. We need a model for the plasma. We need a model for the flow velocity and the magnetic field strength and the density in the region around the black hole. And most of the models that you have seen assume an ideal MHD structure for the flow. And this is a serious approximation. We also need to understand what the initial and boundary conditions are. So other people showed simulations of accreting black holes with cosmological context, or extending out to a much larger radius, and we have to specify that in our models. We need boundary conditions. And then to estimate what event horizon telescope will see, we need radiative transport, and that could be polarized or unpolarized. And to do the radiative transport, we need to understand the emission and absorption properties of the plasma. So we need emission, absorption, and for polarized transport, we need rotation coefficients. And a lot of this, unfortunately, depends on plasma physics that we don't understand very well. So let me give you a sense of what the flow models look like. This is a simulation done by Hotaka Shikawa, who's sitting in the back here. And this shows the proper density in equatorial plane of a black hole, in which the accretion flow is aligned with the spin of the hole. And Yeah, so I don't have, yeah, it's the rest mass density. It's the proper density. So I don't have a color bar for you, but I'm not sure that would be very enlightening. A sort of typical density here is about 10 to the 7 electrons per centimeter cubed. So what you see here is a turbulent, MHD turbulent disk. Things evolve much more rapidly at the inside than at the outside, and there are typically spiral structures in the accretion flow. Okay, so simulations like that form the basis for the radiative transfer models that you've seen up to now. And again, you have to make some assumptions about the character of the electrons, the temperature or the distribution function of the electrons. So let me just say a couple words about that. So the plasma in the regime that we're interested in is collisionless. So that means that the Coulomb mean free path is of order 100,000 times the event horizon size. And that suggests that the ions and the electrons are decoupled thermodynamically. So the ion energy, we imagine, is fixed by the flow model. It's fixed by the temperature from the gas dynamic simulations. And the dimensionless temperature of the protons in units of the proton rest mass is of order 1/10. The electron temperature, on the other hand, is constrained directly by the observation. So we measure the flux, we know how big the source is, and from that we can estimate what the electron temperature is in rest mass units, and it's about 10. So this is a typical Lorentz factor for the emitting electrons. And then in the models, we have to somehow set the electron temperature, and there are a variety of ways of doing that. And I'm going to show you some models that try and understand how the dissipation would be divided between the ions and the electrons and calculate in as close to ab initio a fashion as we can what the electron temperature is. Okay, so I'll show you an animation of this. Okay, so this is a model of Sagittarius A star at 1.3 millimeters. There's no interstellar scattering incorporated in this model. And this is seen at an inclination of 60 degrees to the spin axis of the black hole and the orbital angular momentum of the accretion flow, which are assumed to be aligned. So this is a modestly spinning black hole, and this evolves over the course of about 5 hours, which is similar to the duration of a single EHT observing day. So we're going to run through here and watch the time evolution, and then we'll see this rotate in azimuth, so we get to see it from several different angles. And then we'll see what it looks like from different inclinations. You can see it's bigger when seen pole on. And then we'll scan through in frequency, starting at 1.3 millimeters and working up in frequency. You can see the source become more and more transparent. And then as we come back down, it becomes more opaque. So I think Dimitris showed something like this in his talk. So at lower frequency, the event horizon is hidden by the opaque accretion flow. Okay, so this is only part of the information that's going to be available from event horizon telescope data. So this is total intensity. And of course, EHT is going to measure polarized intensity as well. And I think we're just starting to figure out what the implications of that are. Some people like Avery have been doing polarized transport for years. We've just sort of figured out how to do it. And I'm going to show you here why polarization is so important. So this shows exactly the same model I just showed you with total intensity up here on the left. A different color map, but still total intensity. And then some polarization vectors superposed on the animation. On the right is the linear polarization percentage, circular polarization percentage, and then this thing that looks like TV static is the electric vector polarization angle. And if you integrate over that, you find that the source is almost completely depolarized. So this model, this particular model, is falsified by existing data, which says that the source has a linear polarization of somewhere between 4 and 15%. And that's very interesting, and we understand, I think, a little bit about why that is. It's because there's a cold disk in this model, and the cold disk produces strong Faraday rotation of the polarization vectors. Now, I don't want you to leave with the impression that there are no models that work. So there are some models that work. This is a very old model from the late in the last decade that Monica Mashka-Brushka and I put together, and Hotaka, who's sitting in the back. And this produces about the right linear polarization and about the right integrated rotation measure for the source. And this, surprisingly, uses a less sophisticated model of the electron thermodynamics. Okay, so here's the summary. The constraints on the model include the mass and the distance, and the ratio of mass to distance is the angular size of the hole that's constrained to within 5% by the stellar orbit data. The size from existing EHT measurements, which will become much better in just a few months. The spectrum, variability, and polarization. The models are almost all relativistic MHD models with some kind of superposed radiative transport, in some cases polarized transport. And I think the leading uncertainties in this business are really the magnetic field geometry in the solution that can strongly change the outcome, and also the electron distribution function. So I showed you two models with different assumptions about the electron distribution function, and they produce quite different polarization outcomes. So the EHT polarization maps will be a powerful constraint on the models. Okay, that's it. Thank you.
Questions for Charles? Peter?
I was wondering, in the accretion flow simulations that you do, how sensitive are they to the initial conditions that you start those models, the evolving ones?
Yeah, so they seem to be sensitive to some features of the initial conditions and not others. So the initial state is unstable. It's differentially rotating and magnetized, and so that leads to turbulence. And so it forgets about many features of its initial state. But certain features seem to be remembered, and one of those is the net magnetic flux through the disk. And that's what I meant by field geometry there. It seems to be sensitive to that.
Priya?
Charles, in those disk simulations, how thick is the disk? One didn't have a sense of that, right?
Yeah,
What's
so
the vertical?
The vertical thickness is about 0.3. So ratio of the scale height to the local radius is about 0.3. And I think that's consistent. These models are very localized around the event horizon, but people have done more extended models. I think Ramesh has done one a few years ago that seem to produce similar H over R ratios. Yeah.
Question over there?
So about the polarization, is there a consensus now as to about the circular polarization, whether it's due to intrinsic source or due to propagation effect? Or can you really separate them? What's the current?
Yeah, I don't know the answer to that yet. These polarization
circular
things
polarization.
These polarization movies are pretty hot off the press. Circular polarization is produced by the thermal distribution function at low frequencies, and it can be produced by Faraday conversion at higher frequencies. So I just don't know the answer to that yet.
Charles, a general question about the philosophy of the code. There are two possible ways to radiate for the plasma. One is through the hydrodynamics that you showed us plots of. Another one is in hotspots created by reconnection events, and like we see in solar flares. Those would be much more difficult to calculate in principle. Could you comment on what your thoughts are about the importance of each of these modes?
Yeah, well, so what goes into our model does not take account of heating of electrons at reconnection events. So the idea is that there's a turbulent cascade that dissipates the energy at small scale. And Andrei Belobordov has a recent paper on heating in reconnection events. I think it'd be very interesting to include that, and in fact, I have a student working on that.
Okay, but do you think it could dominate the emission, or is it
Yeah,
subdominant?
so these, just comparing these two models, and it's really too early to draw any broad conclusions from this, but it kind of looks like the electron temperature and ion temperature are fairly close based on the polarization outcomes. And that might mean that our model of dissipation is incorrect and that it's not the turbulent cascade, it's the reconnection that heats the electrons.
Very interesting. If there are no more questions, let's thank Charles. Oh, there was, sorry, behind me. Sorry.
I was wondering if you can comment about the degeneracies between the model ingredients. If there are degeneracies, so if two different models can produce the same features and they cannot really be distinguished.
Yeah, I think we don't understand that very well yet. We have to, there's not much in this that's like LIGO, but there is a sense in which both there and here, it's very expensive to run the models. And so we don't really have a survey numerically of parameter space yet. Now, Avery has produced semi-analytic models that one can scan over, and he can say a few words perhaps about the degeneracy in those models. But I think broadly we have a sense of how some of the parameters affect the images. So inclination tends to affect the image size. So low inclination sources tend to be large. And I think we also know that the spin of the black hole affects the X-ray to millimeter colors. So higher spin produces more X-rays by Compton scattering. And those are two sort of physically motivated parameter dependencies.
Well, this is a perfect prelude for Avery. Thank you again, Charles.
Well, thank you, and thank you to the organizers for inviting me to your excellent black hole initiative. So as Shep stated, we are now at the end of the beginning, and I am as excited as anyone to find out what the first image looks like, and I'm sure it'll be iconic, and we'll weep and we'll cry, but instead, I want to talk about the next stage. So not what happens when we have one image, but what happens when we can make movies and we have many images across many different timescales. In other words, when we have enough images to probe the drama that's unfolding in the vicinity of the black hole. Now, of course, everything I'm going to talk about today is done in the context of now a large and growing collaboration. So all honor and glory belongs to the collaboration, EHT collaboration. Mistakes are purely mine. These are students and postdocs in my group, except for Avi. He's not in my group, but and Mark Reed's not in my group, who have participated in some of the things that I'm going to show today. So the key message, I know we all just came back from lunch, and many of you may not have had coffee. So the key message that I hope to communicate is that while that first image is great, the EHT targets, Sag A star and M87, exhibit structural variability over a wide range of time scales, betraying physics on a wide range of physical scales. And so this is telling stories about the physics of black holes and their interactions with their environments. And I'm going to give a few examples. So while that first image is wonderful, the next 1,000, I think, are going to be the transformative ones. So I'm going to give you a series of vignettes. I'm going to start at short time scales, and then I'm going to move out to ever longer time scales and talk about what exactly we might hope to learn. So I'm going to start on the horizon. Okay, so these are length scales of order 10m or so, time scales of order minutes. These are the sorts of things that in Sagittarius star we would read off of strip charts, although what Shep was talking about with spots. Here's that movie I think Shep was trying to show you. This is Hataka Shikawa's movie that shows a GRMHD simulation of the black hole of the sun and the Milky Way. Now I've rotated it, so it looks a little weird because the spin's pointing off in this direction, and I've done that because that's our favorite orientation for the actual spin, and I'll come to that in a little bit. So whenever you see these things turned over so the bright spot's down here, it's because the spin's oriented in this direction, but the accretion flow is still moving around like this. You can see all the turbulent substructures in here, so hopefully this kind of variability will tell us something important about how angular momentum transport occurs in accretion flows, studying the MHD turbulence within the accretion disk. I'm not going to say any more than recall Charles's talk a few minutes ago. Instead, I'm going to belabor the point that Avi made. The GRMHD simulations to date are really good at modeling this part of the sun, okay, sort of the convective turbulent regions. But as of yet, they don't include the catastrophic particle acceleration that occurs in events like this one, okay, solar flares. And if anything that we think about the kind of accretion flow models for Sagittarius star are right, we should be seeing events like this. Okay, so catastrophic brightening where you dump large amounts of energy into a small population of electrons that outshines the rest. I mean, that's easily possible, in fact, unavoidable, I think, in Sagittarius star's accretion flow. So what might this look like? Well, more than a decade ago, so now I feel old, Avi and I proposed that this might be the origin of the infrared flaring in Sagittarius star, and noted that in these images is encoded information not only about where the flare went off and how bright it was, but also the structure of the space-time, because you see multiple images of the original spot, and the relationship of those images to another encodes things like spin. Okay, a slightly more recent simulation looks like this one here, where you have a spot go off, and then it synchrotron cools and dies away, and a little bit later, you'll get another spot go off. And of course, they're going off in different locations. And because they go off in different locations, you're probing different parts of the space-time. Okay, and so if I were to just pick the two prettiest frames from each of those spots, we're looking at different regions of the space-time around the black hole. So you can begin the process of tomographically mapping out the structure of a Kerr space-time just by looking at the impact of gravitational lensing on these localized emission regions. Moving a little bit further out and switching for a moment to M87, what happens if we inject similar types of things, similar variability within the jet of M87? This is occurring a bit further out just because of the geometry of M87. The jet's pointing towards us, so that by the time it lights up, stuff's already a bit of the ways downstream. And the timescales of order days, not just because of the distance scale, but also because M87 is much more massive. Why would we bother to do this? Well, we are absolutely certain that there's structural variability in M87 because at 7 millimeters, it's this movie by Craig Walker and collaborators, you see features that are moving out, sometimes coherent features that move out on the time scales of weeks. Okay, so we know these things are there. What does this look like to the Event Horizon Telescope? Well, that depends on where these spots are being launched from, where these features originate. Now, unlike that picture I showed a moment ago of a spot in an accretion flow around Sagittarius star, when we talk about M87, it's not as simple as putting in a single blob and letting it propagate outward, because the jet is a highly structured and stratified velocity field. The inner region of the jet moves very fast. The outer region outside of the jet and the wind moves much more slowly. They have very different azimuthal velocities, toroidal velocities. And so if we were to look at spots placed inside the jet, they will rapidly shear. Spots placed outside the jet, say in the disk wind, will shear much less. And you really can't avoid this. If you put in a blob, it very quickly becomes a snake. Okay? So here's a movie that shows spots placed in different locations, okay, spots placed within the jet, so within the part of the jet that might be powered by something like the Blandford-Nyack process, powered directly by the black hole, and spots that are placed outside the jet in a wind, okay, driven by a process maybe more like Blandford-Payne, and something right on the boundary between them. And in all of these, I want to note that the black hole shadow would be down here. We're showing a rather large dynamic range. That's why it's hard to see, but it is still there. If we just focus on the last frame of the movie, these are easily distinguishable. And this is entirely because of what happens to the spot as it propagates out, how it accelerates and how it shears. And one interesting thing about this is like the variability in Sagittarius star, you can read this off of sort of strip chart variables, either closure phase, like Shep showed for spots in Sagittarius star, or even just visibility amplitudes. So you don't need a full imaging array to catch M87 in one of these active periods to see whether or not jets are powered by black holes or by accretion disks. I should note that we've done the same thing in a shearing accretion flow, okay, so a Keplerian accretion flow velocity profile. And here's an example of a spot that stays coherent but does stretch a bit, and you see these nice spiral structures in the image that I think you frequently see in simulations as well. And I think that gives us a little bit of hope that these sorts of features could be modeled by small parameter family objects. So if you wait for one of these bright events, you really don't need to run an entire MHD simulation to understand what exactly happened to that spot. Moving on to timescales of years and pushing outwards to hundreds or tens of thousands of M, there is this period preceding, I think, these extraordinary observations that just happened this past month of about 10 years of what's been called proto-EHT. I think Jim coined the name, the proto-EHT. It's a three-station array. And we've spent a lot of time thinking about what that data might mean. And one of the remarkable things is that a fairly simple model, this is the semi-analytic model that Charles mentioned a moment ago, can fit the data across many, many years. Okay? Fits it fairly well. It gives us an orientation which is fairly well defined. But I think what's really important or really interesting is that if you were to fit each day individually, you would reconstruct the same parameters. You reconstruct the same orientation of the black hole and the same spin. Okay, so this is a plot that just shows as a function of epochs spanning 7 years and the position angle on the sky of the black hole spin, or more properly, the angular momentum vector of the accretion flow. Okay, and that's actually a bit surprising. And the reason is because we have no reason to think that the sources of accreting gas into the galactic center are aligned with the spin of the black hole. Okay, the accretion rate's extraordinarily low, hasn't accreted enough stuff in the recent past to align the spin. The sources of accretion are rather varied, coming from different directions on timescales that vary as short as a decade. Okay, and we know what happens when we have misaligned accretion flows and spins for efficient accretors. We get these Bardeen-Pedersen warps, okay, which twist up the disk. Eventually it aligns it in the inner region. Okay, here's a picture of a simulation done with a moderate misalignment angle of 30 degrees. You can see some of the spiral structure in the warp. Interesting things can happen if you do just hydrodynamics and extreme stream angles. Okay, this occurs in thin disks when neighboring annuli can precess under the action of lens steering precession or lens steering torques independently. But a thick disk is a little bit different. A thick disk is different because it effectively couples neighboring fluid elements with strong torques, presumably magnetic torques. And as a consequence, thick disks don't twist up so much as they just en masse rigidly precess about. Okay, and so here's a nice simulation by Chris Vergil that pointed this out more than a decade ago now. And this has a very clear observational consequence. We would see wobbling on the time scale of the precession. So as the black hole, or as the accretion flow moved around, as it changed its position angle in the sky, we would see a wobbling of the image. in a systematic and well-understood way. And the timescale for that wobbling, it turns out, is just set by the angular momentum in the disk divided by the lens steering torques, and that comes to the scale of years. And remember, we have a decade of proto-EHT data. So we looked at that. We asked what happens if we don't try to fit a single model, but instead a set of models that are characterized by some precession direction, precession axis, some original orientation, and some sized accretion flow, right? The outer radius, this RO, defines how far out the disk can extend and therefore how much angular momentum is in the disk. Okay? And just fit that model. So we have a time variable model that has a slow time variability, a time variability on the scale of years. And we can already say something. I wouldn't claim that this is definitive, but it looks like we can start to rule out disks that are too small. We don't actually see any evidence for precession at the moment. But we can go after things like precession or the origin of the gas for Sagittarius disk in the future, in the coming few years. One interesting feature is that there's a maximum in the allowed probability in this outer radius spin diagram that sits right around the periastron of S2. This is not just a time-scale coincidence. This is actually a century-long precession timescale, and it's about a 15-year orbital timescale. But it's 1 sigma, and so I don't trust it at all. But it's interesting. Okay. And the last thing I want to talk about, this comes directly to the question about Brownian motion, is decadal time scales. We're probing much larger distance scales from the black hole. And it's exactly this jitter motion driven by the retinue of stellar mass objects or stellar mass black holes that surround Sagittarius star. So because you'll get Poisson fluctuations in the total numbers on each side, you'll generate impulses that will push the black hole around. Typical scales for how far it gets pushed around is a microarc second. We heard that the size of this image was about 50 microarc seconds. Okay, so I've exaggerated it somewhat substantially here. In order to do this, you need first the ability to determine where the black hole is. Okay, not the ability to determine where the bright part is, but where the black hole is. This is an experiment you do with the rest mass, and the EHT is uniquely able to identify where the black hole is by locating the shadow. Okay? The second thing is you need to be able to do absolute astrometry. It's not enough to see what happens over a single hour span. You need to do this over many, many years, decades in fact. And so you need references. There are references. But at millimeter wavelengths, the atmospheric coherence time is very short, so you can't nod your telescopes from your source to your reference and back. So you need the ability to subnet, subarray. Okay, so the fact that the EHT is, I think, the only Earth-sized interferometer that's constructed of arrays in its own right turns out to be exactly what the doctor ordered for this. So what would we expect? Well, after some amount of time, you'd be able to construct a power spectrum of these fluctuations. The power spectrum depends critically upon how massive the constituents of the nuclear cluster are, and how many of them there are. Okay, so we can tell the difference between a nuclear cluster composed of black holes, a nuclear cluster composed of stars, a nuclear cluster that's been scoured, or even one for some reason that's completely empty. We could also say something about the origin of the S stars, right? These are these infrared bright stars, B stars, that are orbiting very close to Sagittarius A star. And André Ghez coined the term paradox of youth. It was unclear how you got stars this young, this close to the black hole, and there were really only two solutions. One is form them in a way in situ that we don't understand, and the other was what I like to call the busing solution. You have some cluster that's born far away and somehow falls in. The only problem with the busing solution is that the cluster itself gets tidally disrupted. But you can fix this problem if you posit the existence of an intermediate mass black hole that will hold the cluster together until such time as it can deposit its stars down around the black Sagittarius star. But that means that there would be an intermediate mass black hole orbiting Sagittarius star with a typical orbit similar to those of the S stars, and it would have arrived in the past million years. And that kind of object would induce not jitter, but a secular motion in the position of Sagittarius star that you would measure with this sort of long-term absolute astrometric monitoring. And in fact, the sweet spot where you wouldn't have seen it yet, it wouldn't have coalesced just under the action of gravitational radiation, and it has the right typical separations and periods, is what we could do with about a decade or so of absolute astrometry with EHT type instruments. So here's my key point slide again. There's structural variability on lots of different time scales. I explored minutes to decades here. Of course, everybody has their favorite version of variability to go after. So stay tuned. The end of the beginning has come, but we have a long way to go. Thank you.
Questions? Priya.
Very nice. Avery, if you don't see lens thirring precession, you could use that, right, to give an estimate of how short the alignment timescale is. Right?
Well, so the lens theory and precession timescale depends on three things. One is whether or not they're aligned. Two, the second is what the spin of the black hole is. And the third is how large is the disk. So the timescale for lens theory, if the gas really originates out at the clockwise disk. Okay, so there's this disk of Wolf-Rayet and O stars quite far away that presumably could be providing the gas. That timescale is like 100,000 years. So that might be difficult to just rule out that we have an ever-increasing size disk. It would have been wonderful if we actually had a measurement there, but...
But is the direction of the orbital plane consistent with that origin?
Yeah, that was going to be my follow-up. I mean, are the directions?
That's an excellent question. Give me a second. So here's the reconstructed directions on the sky as seen from the center of the galaxy for the disk angular momentum axis from this 7 years analysis. There are two spots because it's hard to tell the difference between something tilted this way towards you and tilted that way. Okay. So that's one high probability region, that's the other one. There's the clockwise disk of stars. There's G2, okay? G1, G2's little friend. So actually, yeah, I'd call that roughly consistent. So there is sort of a story that hangs together if you were to believe the model class is sufficiently generic and all of those caveats.
We got used to large error bars from the LIGO plots, so it looks pretty good.
The problem with small error bars is you can hang yourself real fast.
Ramesh.
So, Avery, you looked at all the proto-EHT data, used your simple model, and got a few parameters out of it. In that process, did you try comparing models where the radiation is mostly from a torus versus models where mostly it's from a jet? Could you discriminate?
So we have fit jet models to M87, but we have not fit jet models to Sagittarius star yet.
I think this would be an interesting thing. Of course, we are going to know the answer once Sheperd gives us the first picture. But
right.
I would be very interested to know whether your prediction powers are good enough to say whether or not there's a jet.
Well, so I have people working on exactly that now.
Well, if there are no more questions, let's thank Avery.
Well, so Charles and Avery have really summarized the state of the art for numerical simulations of supermassive black holes. And so what I'd like to do to close out this session is to bring it back to the EHT instrument and to really think about what it is that it's capable of, both now with existing data and in the coming years as it expands to maturity. And I really want to do this to kind of prompt you to think about ways in which the EHT might connect to your research. And if you have ideas, you should get in touch. You might be surprised at what we can do. So I'll start by covering polarization with some recent results from the Event Horizon Telescope, and then I'll close out by talking about how the EHT can study dynamics near a black hole. So the story of polarization really starts with the spectrum of Sagittarius star, and both Shep and Charles touched on this. And also we heard from Marta and others yesterday that the scale of these black hole accretion systems is enormous. So in the case of Sagittarius star, the accretion flow starts at the Bondi scale, which is about 100,000 Schwarzschild radii. And as Shep said, the EHT has now identified that the submillimeter emission subtends the size of only about 4 or 5 Schwarzschild radii. And as you can see from the spectrum, what's so special about Sagittarius star is that the spectrum peaks in the submillimeter, which means that somehow this vast accretion system is pumping out almost all of its energy in a region that's about the size of the black hole, this tiny speck in the middle of this incredibly large system. And so the question is, how is the black hole tied to this energetic emission, and what is driving it all? Now, the other thing you notice from the spectrum is that the submillimeter emission is synchrotron. And as Charles showed, synchrotron emission is expected to be highly linearly polarized. So because the EHT can measure polarization, we can make images of the linear polarization near Sagittarius star. So we expect this polarization, but below about 100 gigahertz, Sagittarius star is unpolarized. And that's where every existing VLBI array other than the EHT is operating, which means no VLBI to date has been able to understand the polarization structure of Sagittarius star. Now, as Charles mentioned, we see that there's about 7% polarization coming from Sagittarius star, and this is with instruments that don't resolve the emission. And because polarization is a vector field, we can't tell what's causing this low degree of polarization. So it may be that the fields are pretty uniform. They're ordered throughout the emission region, and that there's low polarization everywhere. But it might also be that the emission region is highly polarized. There it is. That the emission is highly polarized, but that the fields are tangled and disordered. And then if you don't resolve the image, you'll again see a low net polarization because of cancellation across the image. So before the EHT, before we could resolve the image, the magnetic field order near Sagittarius star was unknown. So before I jump into the data, I just wanted to revisit why we care so much about the polarization near Sagittarius star. And the first thing is that it gives us a new probe of strong gravity. So again, the polarization is a vector quantity, and so as it propagates away from Sagittarius star, it has to be parallel transported. And so the polarization direction will be twisted by the curvature of the spacetime near the black hole, and this gives us a diagnostic of the strong gravity that we would completely miss if we only looked at the total flux density. And the second reason is that, as we heard yesterday, accretion onto a black hole is actually very difficult. It's hard to fall into a black hole. And the thing that we think allows these black holes at the centers of galaxies to accrete so efficiently is turbulence that's driven by magnetic instability. So one thing that we'd like to do with the Event Horizon Telescope is look for signatures of this magnetic turbulence so that we can confirm this paradigm of what's allowing black holes to accrete so effectively. And the last thing is that polarization extends our perspective away from this tiny speck at the middle of the accretion flow to the global accretion dynamics throughout the flow. And this is through Faraday rotation. So Faraday rotation tells us about magnetic field strength and plasma density along the line of sight. And so we can connect EHT studies to the larger scale dynamics and understand how black holes fit in a more global context. And in case you don't believe me, I just want to emphasize, Sagittarius star was studied for decades with every wavelength imaginable. And it wasn't until the detection of submillimeter polarization that the accretion rate of Sagittarius star was determined. So even only a few measurements with polarization can be enormously informative. So I'll show you some results that we have with EHT data using the 2013 EHT configuration. This is just a sliver of the completed array with only 3 sites in California, Arizona, and Hawaii. But like the discovery of linear polarization near Sagittarius star, only this sparse array can still tell us quite a lot. So this is our data plotted in kind of a funny way. Each tick here, the x and y coordinates of it, tell the east-west and the north-south baseline. Okay, so that's telling you for a pair of telescopes how long the distance is between them. And then I'm just showing the polarization angle and magnitude on that baseline by the color and direction of the tick. And what we saw on our short baselines, this is from California and Arizona, is similar to what arrays have always seen for Sagittarius star that couldn't resolve it. We see sort of 5 to 10% polarization fraction. And this isn't surprising. These are the shortest baselines, so that means they have the worst angular resolution. They're not actually resolving the emission region. You'll notice there's a lot of fluff along these tracks. And the reason for that is because the source is not static. It's actually changing in time over the course of a single observation. The polarization fields are dancing around in time. Now, when we look at our longer baseline data, the situation changes dramatically. Here, the polarization fractions shoot up by an order of magnitude. We saw polarizations as high as 70 or 80%. And so this is telling us that we're finally at baselines that are long enough to resolve this incredibly compact and highly polarized emission region. Now, this isn't enough data for imaging, but we can still say model-independent things about the polarization near Sagittarius star. So in particular, when you measure polarization with an interferometer, you measure actually two quantities on every baseline. So you can take the left circular polarization at one site and correlate it with right circular at the other, or you can take right circular at the first site and correlate it with left circular at the other. And this is visualized on this figure by the two hemispheres. And what we can do then is we can compare the polarization measurements on these two baseline directions, and you'll notice that they're strikingly different. And it turns out that this is impossible if the polarization direction throughout the emission region is constant. So even if you allow it to be arbitrarily polarized in magnitude, maybe there are some highly polarized patches and a few low polarized patches, that can vary however you like, but you could never see this asymmetry unless the polarization direction had variations throughout the emission region. So immediately, we know there have to be these variations, and that has to be producing part of the low polarization that we measure, that 7% polarization. It's telling us the intrinsic degree of polarization must be much higher. Now, we can make this a bit more concrete by plotting data in even a more funny way. And this is plotting two dimensionless quantities against each other. So on the x-axis is the correlated flux density. This is telling you how heavily you're resolving the image. Longer baselines will push to the left on this diagram. The y-axis is telling the fractional polarization at those scales. So it's telling you how polarization dominated your power is at those scales. So to give you a few examples, suppose that there's just uniform polarization across the image. In that case, it doesn't matter the scale you look. You always see the same relative dominance of the polarization power. And so you'll see this flat line at the bottom. On the other hand, suppose that your fields are completely tangled and disordered. Now, in this limit, as you look at smaller and smaller scales, the flux will start to look smooth, but you're not resolving the small scale changes in polarization direction. So as you go to smaller and smaller scales, you're increasingly polarization dominated. And so that's this other asymptotic limit for turbulent fields. And we can look at those three models from earlier, and remember, these all appear identical to an array that doesn't resolve the source. Model A, in this case, is close to that ordered field limit. Model C is close to the turbulent limit. And model B is actually compatible with the EHT data, and it's giving you a sense of the relative balance between order and disorder that we see in the polarization structure near Sagittarius star. Now, of course, the next steps for us are to go from these kind of model-independent metrics to complete imaging. And we've already seen a few very nice examples of the image reconstructions you can do with the EHT. But there's something missing there. It turns out we can't make an image of a black hole with 7 sites, or 8 sites, or even 9. You just can't do it. We need an extra ingredient, and the trick that we bring is that we make the Earth part of our instrument. As the Earth is rotating, the projected baseline between different sites changes over time. And so we can build up frequency coverage of our image. And so by collecting all that information over an entire night, that's how you make an image. So here's a simulated image and a reconstruction in the middle, and I'm just going to spin the Earth, and I'm going to collect all the baseline coverage as it's spinning. And I'm going to build up an image that uses all the frequencies before. So it starts out pretty poor, but over the course of a night, you get all that frequency coverage, and you end with a nice image reconstruction where you can see features like the shadow. So this is a standard technique in VLBI. This goes back decades. And the problem is it breaks for Sagittarius star. Sagittarius star introduces something new to the game, which is what Avery talked about, time variability. We expect Sagittarius star to be changing on timescales of minutes, whereas the Earth is evolving on timescales of hours. And this is really unprecedented. Most sources that we look at with VLBI change on timescales of months or longer. And so what we have to do is develop new techniques to accommodate this variability and to somehow still make images even as our source is changing. So of course, the natural extension here is to, instead of making static images with EHT, to try to reconstruct movies. So here's an example. What I'll show you here on the left is the simulation from Avery and Avi of a hotspot trapped in the accretion disk near Sagittarius star. And this hotspot's going to be absorbing, this hotspot has an orbital period of about 27 minutes. Over this time, the Earth hardly rotates at all. There's no time to build up frequency coverage. But what we can do is we can take this, this data, and instead of reconstructing a static image, we reconstruct a movie from the full set of data. And by linking together our frames and saying that there has to be continuity of moving features from frame to frame, we can buy back that trick of using the rotation of the Earth and building up frequency coverage by forcing it to all go together into a single coherent movie that takes all of the data. And so ultimately, once the EHT is complete, we'll be able to track flaring structure in real time and be able to study this from an imaging perspective. Now we're even pushing beyond this. So instead of thinking of the image as, say, just a collection of pixels, we've started to think of it as maybe a fluid. And so you can take this image and you can let it evolve as a fluid with some stable flow. Maybe it's still stochastic. There's a lot of irregular stuff, like in an accretion flow, but perhaps the underlying evolution is dominated by a fairly stable motion field. And so here, this is what we're doing. You can see that the reconstructed movie, again, can pull out lots of the bright evolving features, but it can also start to lock in on the details of the flow that's driving this system. So ultimately, the EHT might even be able to do things like studying rotation curves near the black hole and to really pin down the dynamical activity near the horizon. I want to emphasize, this work was done with a lot of people, and the BHI is kind of built on this idea of multidisciplinary approach to science being effective. And I think, there's a lot of skepticism about whether that can work. But this particular idea of dynamical imaging, you can see it involves, Andrew Shale from Harvard Physics, Katie Bowman from the MIT Computer Vision Department, Lindy Blackburn, Andre Young, and Kazuo Akiyama, who are all astronomers, and then also Julian Rosen, who's actually a mathematician. And I think we could have come up with something just staying within the astronomy community. I think we would have figured some technique out that did okay. But by drawing upon the expertise of all these different disciplines, it dramatically accelerated our project. VLBI is an old community. It goes back decades, and we've developed this entirely new technique on a timescale of months. And in addition to accelerating the progress, I just think the outcome is so much deeper than it would have been if we had stayed within our own community. So I hope that this can be kind of a model for the types of things that we can learn within the BHI community as well. So just to summarize, the EHT is not a completed instrument. It's been built up over time, and it will continue to develop. But even with an incomplete array, we've already learned a lot of things that are model independent. We've learned that there's an extremely compact emission region in Sagittarius star that's producing most of its flux density. And this emission region subtends a size of something like 4 or 5 Schwarzschild radii. We've also seen that there's persistent asymmetry in the image of Sagittarius star over multiple years. The gravity of the black hole is imprinting itself upon the image, and we're not just looking at some featureless blob on the sky. We've detected that there are ordered magnetic fields near the event horizon, and we've seen that they're intensely variable. And over the next few years, there's every hope that we'll be able to make the first images of a black hole and also be able to make movies of the dynamics that's going on near a black hole and to confirm directly whether these models, like what Avery's shown, are really happening and whether it looks like the surface of the sun bursting and boiling. We can also study linear polarization, Faraday rotation, and there's plenty of other targets for us as well, including M87 with a booming jet, OJ287, which might have a binary supermassive black hole, and these other monster black holes that Chung-Pei Ma talked about, like NGC 1600. So, the EHT, I think the future is bright for the EHT, but the future is also fluid, and I really hope that it will continue to evolve and adapt to the science cases that we identify through collaborations and conversations at the BHI. So I look forward to talking with you more about future possibilities.
Michael, I noticed that you didn't have a philosopher in your team. You might want to add that.
Absolutely.
Ramesh.
as always, the movies are great, Michael. So, but do you think you can do this complete animated movie image or whatever with polarization? Can we actually watch the magnetic fields twisting and turning and wrapping around?
So polarization actually brings a lot of information to the observables. So the answer is yes and no.
Okay.
I think we will be able to make movies of the polarization, and I think that they'll be stunning and spectacular. I worry that all the twisting and moving will be because of the Faraday rotation. It's hard to say how confidently we'll be able to link it to the horizon. Now, the EHT is expanding its bandwidth, and so we should be able to confidently measure the Faraday rotation and remove it. But I would say the timescale to make polarization images and really have any idea of what we're looking at, that's a 5-year timescale probably. It's going to be a very difficult problem.
Okay.
Yeah.
Because, the dynamics of the magnetic field, I'm sure Charles would love to see what the real thing looks like.
Well,
we do it on the computer, but we have no idea if the real object looks like that or not.
And I'm becoming more and more convinced, if you look at a snapshot from these simulations, it's pretty hard to tell what's going on, even for experts. The dynamics is what's telling us what's happening near the black hole, what these structures are, how they form, how they dissipate. And so, making movies of polarization has eluded us, but I think once we add a philosopher, we'll be there.
But actually, the dynamics offers another important ingredient, which is you're looking at a projected image, so there could be things along the line of sight, not necessarily close to the black hole, but the timescale for variations far away from the black hole are much longer. So if you see short timescale variations, you know that it must be close.
So this was done in the past for Jupiter, that they actually reconstructed using interferometry 3-dimensional images of Jupiter. And I think one extension of this would be to actually try to make a 3-dimensional model of Sagittarius star and make that. There are many things that we should try in the coming years.
Yeah, there was a question in the back, and then Andy. Yeah. Donglai.
So the toroidal field is a possible, probably likely configuration when you have rotating disk, right?
Yeah.
Toroidal field is ordered, but it's also varying depending on your viewing geometry.
Yeah.
So I just want to get clear, when you say order the B field, do you allow for that toroidal configuration, or do you really mean that the large scale toroidal field going through the horizon?
So it could absolutely be the case that the order that we see comes from a completely turbulent disk that has order imposed by the field shearing out in a poloidal accretion disk. So we cannot discriminate between poloidal order in a jet or toroidal order in a turbulent disk. So yeah, that's absolutely a possibility, which I actually think would be the more physically interesting one.
Andy.
An elementary question. What would you have seen if every photon in 2013 from Sagittarius star had been right circularly polarized? How would that have shown up on your...
Yeah, so it turns out the EHT, it is a full Stokes instrument. So we can, and I didn't talk about it, but we will be able to make images of linear polarization and make images of circular polarization. The reason, it's a technical reason why linear polarization is something we can measure robustly right now, whereas circular polarization requires basically better calibration accuracy than what we have. But for instance, if it was completely circularly polarized, we would have measured that. We can constrain the circular polarization to be less than 10% or so.
Okay, you can measure it. It wouldn't have shown up on that plot you made, but...
That's right. And Jim and others have measured the circular polarization. So we know the image average circular polarization is about 1%.
So like for M87, which is kind of, the axis is along the line and it's probably spinning, you might expect one direction to be preferred over the other.
Well, and this is an interesting point, that the circular polarization of Sagittarius star has remained constant in sign for a long time, a decade or more, which means somehow there is a stable magnetosphere. If it was just pulling in magnetic fields of random sign over time, the circular polarization would be flipping in sign. And so these are again pointing to some sort of stable long-term magnetic field structure. Yeah.
And you'll be able to resolve that polarization as a function around the ring in some sense?
That's right. So this image that's shown, we will be able to make images of Stokes QU and V, of linear and circular polarization with approximately the same resolution. Yeah.
We have to keep in mind also that there are claims that Sagittarius A star flared dramatically 100 years ago from echoes.
Yeah.
And so we are lucky right now to be able to look through all the way, but if there is an increase in the accretion rate that could happen over a century timescale,
yeah.
Things could change dramatically, so we should take as much data as possible before that happens.
Yeah, we have a short window of opportunity.
And of course, the photons we see now left the source 24,000 years ago.
Yeah, it's all old news.
Yeah, it's old news. Any other questions? Erwin.
At what level do you think you'll be affected by what goes on between us and the black holes?
Yeah.
In terms of depolarization, Faraday rotation, things like that.
Well, so this is a very active area of research. I think there are two key things that affect our measurements. One is if there's some Faraday screen that's maybe somewhere between 100 Schwarzschild radii and much further away, which will twist the polarization direction. And again, the EHT should ultimately have enough bandwidth to measure that and invert it from the data. The second effect that does affect our imaging is scattering in the interstellar medium, and this happens much for kiloparsecs away. And this is, again, a very active area of research that we're trying to develop the optimal scattering mitigation techniques. And these are both things where I think we're confident that we understand them and can account for them and invert them and so forth. But if they ended up being deal breakers and we just couldn't do anything about it, then there'd be much, much weaker effects at 345 gigahertz. So, in the natural evolution of the EHT, all of these problems will continue to go away. Yeah. Yes, and we also have fallback sources.
Okay. Peter.
We mostly discussed rotational flares. You mostly discussed rotational flares in the Sag A star. Would you see dynamical changes in the jets of MAB7 too?
Yeah, so I think these movies that Avery was showing, those are tremendously exciting, and I think we can already connect to them with longer wavelength observations. The trick for M87 is much easier. We just make a picture each observing epoch because the evolution timescales are hours or more. The difficulty is we have a pretty short observing window, so we can't watch many orbits or watch flares evolve as much. So again, I think it's kind of nice that we have two sources to look at, each with their own benefit. But I think we'd absolutely be able to see material being launched into jets. Yeah.
Yeah. Two sources that are very different in nature.
Yes.
Yeah. Oh, Misha.
You kind of said about that a little bit, but the question is how strongly interstellar scintillations will affect your polarization signal? Will it help or will it actually make things worse?
Well, I know you have ideas about using it, to our benefit, and Avery has also worked on this. One nice thing is for the particular polarization metrics I showed you with actual data, those are unaffected by scattering because scattering's not birefringent, and so you can use the fact that it'll affect all the polarizations equally to sort of cancel its effects. At this point, it doesn't seem that there are any deal breakers from the scattering. We can simulate it, we can study it. Our knowledge is improved by things like the galactic center magnetar. So I'd say it doesn't seem to be a deal breaker for us, but it's something we're working on.
Another question?
Just
one
comment.
Comment. Yeah.
So I think it's fair to say we're all very excited by these possibilities and the new data. I just want to caution everyone. We have no idea what we're going to see. Yeah. I want to get on top of the expectations here. It could be that we'll take multiple epochs to tease out an image. It could be that we need more algorithmic development. So we're excited and optimistic, but we have no idea what we're going to see.
Shep, you cannot suppress the enthusiasm of theorists. There is no way you can do that.
This is what
irrespective of what you say, we will be excited.
This is what I'm afraid of. This is what.
And we are absolutely equipped to see a snowman. Yeah.